back to the continuation of our review of deep learning papers, most especially in computer vision, and we narrow down to object detection. Now, in this paper, we're talking about the imbalance problems in object detection, and it's a review of the imbalance problem. For those who don't know about the imbalance problem, it's just self-explanatory. It means that, say for instance, you have two classes in your data set. Uh, one class is much more than the other class, so we say it is imbalance. But one very straightforward question is, when do we actually say a data set, for instance, is imbalanced? That's a question for the community working in researches in computer vision. And I'm happy that they mentioned that question in this paper. And that is, how do we quantify imbalance? Uh, that is an open issue. Is how to quantify an imbalance. Okay, so uh, yeah, um, just a second. Talk about how to quantify imbalance. Yeah, so measuring and identify imbalance. So another critical issue that has not been addressed yet is how to quantify or measure imbalance. And as of today, this paper is this year 2020. So how do you say that uh, a data set is actually, when do you say that a data set is actually imbalanced? Let's say for instance you have two classes. One class you have 2000 samples, in the other class you have 2000 samples, and definitely you can say that is a balanced data set. But for the mere fact that you have 2000 samples on each side does not mean that that data set is balanced, because if I have 2000 different samples of, let's say, class 1, and I have almost 1500 duplicated samples in class 0, will you say that is still balanced even though they are all the same 2000? So it's a critical question. How do we quantify, how do we measure imbalance? That's an open problem. Yeah, so we'll come back to that soon. So here in this paper, we're trying to review a number of imbalance problems in object detection, and quite there are a lot, and some of the solutions that have been identified. So they identify major open issues regarding the existing imbalance problems, and those have not been discussed. And they provide a web page which catalogs papers addressing imbalance problem, and you can check that on this link. Okay, so we know that object detection tags is basically two tags: image classification followed by bounding box regression. So you need to first of all estimate what category and also the location of that object. And object detection is applicable in a number of tags applications. For instance, in surveillance, you may want to have a camera that will actually be able to spot um, incidents or spot a particular portion, monitor a particular session, a particular area of a vicinity. So, or to monitor when something actually approaches a particular vicinity. So that's the object detection in using it in surveillance. Uh, Maybe you want to detect when a thief is trying to break into a house or a door. So you must be able to detect the thief. You must be able to detect that the action is breaking into the facility, and so that the camera can take appropriate uh, actions. Because in autonomous driving, we have that. In medical decision making, where you need to perform surgery, you may have some devices that will help to locate where you have the fractured bones or injuries, or where the doctor needs to cut. And of course, many applications in robotics, in picking objects in assembly plant, in factories, in industries. So, imbalance problems in general have a large scope in machine learning, in computer vision, and pattern recognition. And you will see in this table, I talk about the imbalance problems that they reviewed in this paper, and they fall into different categories. The most obvious common one is the classes, where you actually talk about the foreground class imbalance. It is the one that is very common. In other words, okay, you're saying you want to detect cats and dogs. So how many cats, how many dogs do you have in your data set altogether? But you also have the problem of imbalance in foreground background class imbalance. This is talking about your foreground contains your object of interest, but then you have backgrounds that contains other objects that are not your interest, and most times the background are the majority, are more than your object of interest. So this also affects the performance of the model. Of course, you have the scale as well. That talks about, that could be divided into two levels, at the object and at the feature level. So at the object level, you can have, for instance, I'm working on a project on detecting electrical damage in electrical insulators. So now, what I discovered was that when I trained my model, my object detector, on the full image, I was not able to use the model to detect the defect when I actually cropped the insulators. So that talks about scale. Scale is a problem. At what scale, what your data set, if your data set contains different scales, that may be a problem in learning. For instance, if most of the objects in your data set are like, the size is maybe 100 pixel by 500 pixel, then you have some of them that is like maybe it is 5 by 10 pixel. That will affect the learning process of the object detector. So then you also have similar thing in feature level imbalance. I have not worked on this so much. Spatial, I've not worked on spatial so much, on imbalance in spatial. Then you also have the objective imbalance. This is another important one which we will see later on. The objective imbalance is a deliberate bias towards one class, essentially the minority class. So, because as we'll see later on, the object detection task involves multi-task loss, and so there are various components of the loss function that you need to optimize, and you might be biased based on what your preference is for that particular task. We'll soon see that. So the aim in the paper is to present and discuss imbalance problem in object detection. Okay. Now, some of the frequently used notations in the paper, as you can see the symbols. Yeah. The B represents the random box, and C represents a set of class labels in the data set. Say for instance, class 1, class 0. So those are some of the things that we see that. Okay. And it is worth to know that U is a subset of the class label, which is the class label of the parent chart. Now, we're just going to a high level of this paper. In subsequent review, we will begin to now take some little portions of these papers and expand more on it for better understanding. So basically, there are two state-of-the-art in object detection. You have the top-down approach, which is what we are used to, but there is another approach, which is the bottom-up approach. That's essentially introduced by Jeffrey Hinton with the capsules network. I stand to be corrected, but that's my intuition. The top-down approach is what we have, and what it does is, the top-down approach is that in the top-down approach, holistic object hypothesis, that is the anchors, which are essentially the bounding boxes, the region of interest, that is where exactly the spatial position in your image that contains your object of interest, it's also referred to as a proposal, are generated. So we generate those places based on some metrics, and you now are generated and evaluated early in the detection pipeline as to whether truly they contains the object or not. But in the bottom-up approach, holistic objects emerge by grouping sub-object entities like key points or paths later in the process. Like I said, this follows the capsules network, where for you to be able to, for instance, detect a house, you may want to be able to detect the roof, detect the walls, and be able to build them together to know that this is a house. So here is a common training pipeline of a generic detection network, and it involves 3 phases. And the 3 phases are: number 1, the feature extraction. The feature extraction means that the feature, you're trying to do feature map extraction, or what you also call the activation map extraction. Then you do the detection, then you also do the bounding box matching, labeling, and sampling. Now, what does this mean? So you are given an input image which contains different objects. Some are your object of interest, some you are not interested in. So you pass this object through a set of object detectors. Essentially, you use object detector built on convolutional neural networks, a set of conv layers, conv nets. So you extract the feature. The feature we're talking about is essentially a set of numbers, so matrices. Then, based on that feature, uh, the feature map, you can now do both classification and regression. So you do classification based on the anchors, then you do regression based on drawing bounding boxes around the object, making sure you're able to accurately localize the object of interest in the feature. All this involves loss functions optimization. Okay. The top stage here says the bounding box matching, labeling, and sampling. I'm not too sure I quite understand what they were trying to detect, say in this place. So I will leave that out. So this is illustration of example imbalance from each category for object detection. So this is talking about scale imbalance. For instance, you have less you have the blue ones are smaller compared to the ground truth. You have the objective imbalance. This talks about the loss function. You have the class imbalance. Definitely you have more red than green. So this talks about the number of samples of the classes. You also have the spatial imbalance. Like I said, I'm not too clear about spatial imbalance. Maybe in subsequent walkthrough of this paper, we may look at it in details. So definitely the underrepresented class is the class which has less samples in a data set or in a mini batch, and that's another one. This is another very interesting thing to look at, because there was a paper we reviewed. If we go to our archive on paper review, and that paper is curriculum learning, we discovered that in that paper review we mentioned that the performance of a model is affected by the ordering of the samples. That is the way we present the samples to the model during training. So if we just randomly present the samples compared to when we carefully curate the samples by some metrics, that is, we start from the easy samples, then we gradually move to the more difficult samples. If we are able to do that curation well, then we discover that the model performs better, because the model tends to start learning with the easy samples and become good at easy samples before it moves on to more difficult examples in the training. That same intuition is also seen in another paper we reviewed, which is the progressive growing of GAN, generative adversary network. And the idea behind progressive growing of GAN is you have a particular scale of target scale of the image you want to synthesize. Let's say 1024 by 1024. But what you do is that you progressively grow your GANs such that you first of all try to scale down your input samples. That is the 1024 by 1024. You scale it down to something like 4 by 4, and you present that to your network so that your generator which is being fed with random noise, set of vectors randomly, can be good at generating the 4 by 4 before you increase it to 8 by 8, 16 by 16, 32 by 32, 64 by 64, 128 by 128, 512 by 512, until you get to 1024 by 1024. And surprisingly, that approach worked, and that's why you have the progressive growing of GAN being able to generate realistic fake images that can fool humans. So that's what is being said here. The class which has less samples in a data set or mini batch during training in the context. So not just in the data set but also in the mini batches, because essentially when you are training a network, you don't feed in the entire data set. Let's say you have 2000 samples, you don't feed in the 2000 samples in your training. You break those 2000 into mini batches. Say you break it into 128 in each batch. So the first iteration will be 128. You use 128 of those samples to optimize your loss function. Then you pick another 128. So the point this is saying is, if your 128 is skewed, that is imbalance, that you have more classes than the other, that will also impact the training in that. So we're saying that in that 128, we should have roughly, if we are considering class level imbalance, that you have 64 of class 1 and 64 of class 0, for instance. But if we have 120 of class 1 and you just have 8 of class 0 in that mini batch, then that training iteration will be biased. So that's what this is trying to say. I hope that makes some sense. Okay? So this is essentially saying intersection over union of the predicted bounding box and the ground truth. So the predicted is the one that has a bar, and the ground truth is without a bar. And you use intersection over union, which is essentially we can call it the Jaccard coefficient, to be able to estimate how well the prediction has performed. Of course, we know the set of predefined bounding boxes anchor. You see this in our tutorials, we mentioned that before. And in subsequent review, we may look at this more problem-based categorization of the methods used for imbalance problem. And this is just an overview of it, but we may come back to that in later discussion. Moving on, this shows the number of papers by imbalance problem category over the years. Essentially, you have more in class imbalance, which is talking about the number of samples in each class. That's where most people focus on, but you also have some other scale imbalance, spatial imbalance, and objective imbalance. So these two types of class imbalance have different and have been addressed using different types of solutions. So we're talking about the first imbalance problem. Number one is a class imbalance. So we want to look at, they're trying to look at that problem and see the solutions that have been provided in research works. Like I mentioned, that we have the foreground, background class imbalance. So that is in the foreground, background, the underrepresented classes are foreground, the foreground classes. That's actually where your objects are. But the background are overrepresented. You have too many background, too many noise. So they tend to overwhelm what is really your object of it. The foreground background imbalance problems occurs during training, and this does not depend on the number of examples per class. So this is an important thing, like I said. So this is a problem. So for the mere fact that you have the same number of samples in the class or data set, this problem is bigger. Illustration of the class imbalance problem, you can see is overwhelmed. You have too many background compared to foreground. So we will go into details in subsequent reviews. Some of the ways by which this problem are solved: add sampling method, subsampling method. Okay, so moving on, we will add we'll go into this later in another review. Another way of overcoming the problem of the imbalance, the class imbalance, is instead of using the sampling based and sampling free methods, we also have the generative methods to address imbalance, and this works by synthesizing artificial samples and adding it into the training data set. Essentially, you synthesize a minority class so that you can augment it. So we can also go into details for that later. You also have the foreground imbalance going to the batch. So this is what I said earlier. The degree of classing in a batch may be uneven, and that will introduce bias in the learning. Essentially, the way I look at the deep learning framework is, you have students in a class who are trying to learn a new concept, say for example a new subject. Now, at every class, each class, if you are supposed to have like 10 classes, in each class you are actually giving them a mini batch of the entire syllabus. So if your training in each class is uneven, then the students unknowingly are going to be biased towards what you actually spent more time on in each class. That's the way I see it. So I don't know the way you see it. To illustrate the batch level program balance, we provided a figure there, and we'll come back to this in later deep review for us to be able to see it. So moving on, the open issues. You will see here illustration of batch level class imbalance. For instance, this is an example that is consistent with the overall data set. Here is in class A. You have a person class has more instances and packing methods. So these are persons. This is a packing method. Very difficult to read here. But then, an example that has a different distribution from the data set. You will see you have more packing methods here. More packing methods. 1, 2, 3, 4, 5, 6, 7, 8. Then you just have just 2 people. So this is definitely a bias that will affect each batch. So if you put in, even if you check the batch uh, size to be 1, in that batch size of 1, this during training it will favor more. If you put this one during training, it will do better in identifying persons compared to packing it. But if you put this on during training, it will do better in identifying packing meter because it's seeing more of it compared to person. So we also have the ranking based loss functions, which will postpone the scale imbalance. Yeah, this is another interesting one. The object box level scale analyzes the problem arising from imbalance distribution. We postpone that too. So yeah, the feature level imbalance. Look later on into that. It's high level diagrams of the method designed for feature level imbalance. We will also postpone that. So in wrap up, you have a list of widely used loss functions for bounding box regression charts. It's an important one for us to look at. You have the L2 loss and L1 loss. If I can remember correctly, I think we have a tutorial on our channel that discuss either of these loss. You may want to look into it. Then there are some other losses too. Pullback labeler loss is very common in literatures and some other losses. So then you have IOU distribution imbalance. Is observed when the input bounding boxes have skewed IOU distribution. Object location imbalance is another interesting one. The distribution of the object throughout the image matches. Why? I'm currently working on electrical insulators in power lines, like I mentioned earlier. And when you take a picture of the power line, it's essentially that roughly the position of the insulators in the power line will be more or less in the same spatial location. But consider a situation where the location of the insulator is now in corners rather than being in the center where the power lines are. That can affect the learning process too. So we're saying where the object is located, commonly located, because the neural network can just memorize that, okay, once it's 5 pixels to the left and 10 pixels from the top, there will be the object there. If that is where the objects are throughout during training, it will just continue to memorize just 5 pixels from the left and 10 pixels from the top, rather than actually. So if this is my top, so this is from here to here is 10 pixels, and from here to here maybe it's 5 pixels. It will just memorize this place that the object is always here. Maybe that is what you have during training. But during inference, if the object is bottom 5 and from the right, if you swipe it, there is always here, then it will miss the object. So the distribution of the object throughout the image is matter, because currently object is employed densely sampled across a sliding window classifier. So each part in the image is considered with the same importance level. That's what we're trying to say. So the figure in 13 shows an imbalance about the object location. We aim to learn location scale as a ratio of the anchor container to the physical container. So this is a figure in 13. We'll look at that later. So running out of time. The objective imbalance pertains to the loss function. We mentioned this before, and we mentioned that object detection is multi-chance loss. So to solve the two problems simultaneously. Then this is still talking about the objective function, and mention that there's one way you can actually address the imbalance problem based on what you see in other problems, like in image classification and metric learning, is you can have what you call, you will sample the data set either by oversampling or undersampling, or you can use mode or Anderson, or you can do a little bit of trick of transfer learning, and such that your resulting network will be fine-tuned by using a balanced subset of the data set. But after that, after you have trained the network with the entire imbalance, so you hold out some set out of the entire imbalance and you will use the value. The weight loss function to give more weight to the underrepresented curves. Metrics learning, and then I've mentioned the open issues for the imbalance problem. Okay, I think this is a good point to wrap it up here. We will continue from here in the next time. We will look at some of the important ones and try to dig deep into them for better understanding. Thank you for listening, and do give us a like, and please subscribe for subsequent discussions, and thank you. See you in the next one.